So I'm going to just make a video here about the last subtopic, the Big Bang Theory. We don't go into this in a lot of detail, but just so you know, there's the theory you should be familiar with, and then there's two pieces of evidence that you should be able to talk about and discuss. So the theory itself is simply that all of the matter in the universe was once in one location, was condensed into one location, and then there was a explosion or Big Bang, and it exploded and started to expand. Okay, so that's the theory. The theory is simply all the matter in the universe was in one location, and then you could say I wouldn't say it big banged, but it exploded and started to expand. Expanded. Okay, and so the two pieces of evidence that we use for the Big Bang, or that you guys need to know about, there's lots of other evidence. The first one is called CMBR, and that stands for cosmic. All right, C, microwave is the M, microwave background radiation. All right, you can use the abbreviation CMBR, that's an accepted abbreviation, but you should definitely know what it stands for because sometimes they like to ask that. And cosmic microwave background radiation is simply the idea that if there's an explosion, then you should have a release of energy. And remember that waves are a transfer of energy. That is what they are. And so this is actually, it's an interesting piece of evidence because this is something that the scientists cosmologists actually predicted would be there. They said, okay, if we look at how old the universe is and the explosion that we think happened and all these kinds of things, then they said, we predict that the waves, as the universe expanded, then the waves that were released from that initial explosion would also expand. And they predicted that they would find them in the microwave array of the EM spectrum. And they looked, and in fact, they did find them. So cosmic microwave background radiation is exactly what it's all right there in the name, right? They are microwaves, and they are the part of the background radiation. So that means that anywhere in the universe you point a telescope, if it can detect microwaves, it will detect these low-level CMBRs, right? Yeah, so they're in the title. And so the idea is that these are present everywhere in the universe. Anytime you point a telescope that can detect microwaves out towards the universe, out beyond the Earth, then then you will find these. So the present, if it's sensitive enough, obviously. So they're present in all directions in the universe. That's the key. Universe, sorry. So that's the first piece of evidence. Okay, the second piece of evidence is what we call the redshift and the blue shift. Okay, and redshift and blue shift is just another, so if you remember back to the Doppler effect, which there's a video on that I've done, the Doppler effect is the change in frequency and wavelength that you observe from waves when the wave source is moving. And so that's what this is, just in the light spectrum, the visible light spectrum, right? And so the idea is that redshift means that the shift in wavelength is going to be towards the red end of the visible light spectrum. So that is a longer wavelength. So this is the shift that you observe if the object is moving away from you as the observer. All right, and the blue shift is, it's moving towards the shorter end of the spectrum. Remember that when an object is coming towards you, then the wavelengths get squished together, right? So their wavelength decreases, right? And so this is if the object is moving towards you. Oops. So this is the Doppler effect. If you don't know what I'm talking about, go back and watch the Doppler effect video, all right? But it is the Doppler effect, but it's within the visible light spectrum. And so what does that actually look like? I tried printing some out and it didn't really work, so I'm just gonna use the book here, okay? And I'm hoping you can see this. So the idea is that this is what we call a light spectra, okay? And the idea is that this is the sun, Okay, so, and these bands are actually, this is a spectra of hydrogen. So we know that the sun contains hydrogen, and you don't need to know the details of how this works, but this is the normal spectrum for hydrogen. Okay, and so you can see that there are dark bands here that are present throughout. Each element has its specific set of bands, all right? So you look at this, you say, okay, I know hydrogen is present in the sun, all right? Then if you look at a nearby galaxy, what you can see is that the bands have shifted slightly to the right, towards the red end of the spectrum. That's a red shift, okay? And then if you look at a distant galaxy that's further away, then they've shifted even more, and a galaxy that's really far away has shifted even more. So you get these enormous shifts in the wavelength, the spectra of within the visible light. And so the idea is that these shifts, they're all towards the red end of the spectrum, so they're red shifted. And it's not just that objects looking at, so if you think about when something explodes, right, then not only does everything start to move away from each other, but also the things that are on the outside of the explosion move the fastest. And so that is what is happening, is that the further we look, when we look at things that are further away from us here on Earth, then they are redshifted more, which means that they're moving away from us faster than things that are close. So I'm going to write that down. So when we talk about redshift, it's not just the fact that you get redshift. Redshift as evidence for the Big Bang Theory is that the further away an object is, the faster it is being redshifted, the faster it is moving away from us. So further objects, and by objects, I mean, galaxies, stars, things like that. And further away from us, right? Further objects are moving faster, as evidenced by a greater redshift. All right, so that's the second piece of evidence for the Big Bang Theory. Right? Now, there is an equation that you need to know, or sorry, you don't need to have it memorized. You do need to know how to use it for this section. All right, and that is, it's called the Doppler equation. All right, and it sounds confusing, but it's not. So basically, the idea is that you're looking, so you can tell how quickly a galaxy is moving away, or a star, or whatever. Okay, so if you want the velocity of an object that has been redshifted, you can determine that. And you determine it by looking at the change in wavelength. Remember that this symbol is wavelength. That's back from Unit 3, waves, right? So the change in wavelength. So what that means, let me show you again here. Okay, so that means that if the sun, which is not moving away from us, for example, this thick band is probably about what, 390, okay, and then this is about 490, this shift from the galaxy. So the change in wavelength there would be 100, 490 minus 390. Okay, so that's what I mean when I say the change in wavelength. The change in wavelength is the difference between the wavelength, it's the reference wavelength, the sun or something else that you can look at here on Earth that's not moving away from you, versus the actual object that you want to know about. So this is the change in wavelength divided by the reference wavelength. Yeah, I'll write it out in symbols first, and then I'll write it out in words down here. Okay, so this is the reference wavelength. So for example, in the example I gave you, that would be the sun, right? So you would have 100, because that's 490 minus 390, divided by 390, which is the reference wavelength for that part of the spectrum. And that is equal to the velocity of the galaxy divided by c. And c, as in E equals mc squared, this is the speed of light. All right, so I'm going to write that out in words down here. So it's the change in wavelength divided by the reference wavelength. That's the one that's not moving away from you. And that equals the velocity of whatever it is you're looking at, the galaxy or the star, divided by the speed of light. And you don't need to know, they will give you this number. It's 3 times 10 to the 8th meters per second, but they will give you this number if you need it. Okay. So yes, that is the equation. So this is called the Doppler equation. You do not need to have this memorized. It is provided for you on the equation sheet, but you certainly need to know how to use it.